Germain Henry Hess made one of the great discoveries in thermodynamics. He found that the heat evolved or absorbed in a chemical process is the same whether the process takes place in one or several steps. This is because the amount of energy depends only on the states of the reactants and the states of the products, but not on the intermediate steps. Delta H and delta E are independent of reaction pathway. They are state functions. Hess's law can be applied to calculate the enthalpies of reactions that are difficult to measure, and as a result we have enthalpies of reactions tabulated for thousands of reactions, some of which have not even been determined experimentally. The basic idea is that if we want to find the enthalpy of reaction of reactants A going to products D, we can determine that by going from A to B, from B to C, and from C to D, and adding up the associated enthalpies of reactions. Now there's a couple of rules, and one is that if you multiply the reaction by an integer, you have to multiply the delta H of reaction by that same integer. And if you reverse a reaction, then the sign on delta H also is reversed. Here's an example. We have a reaction of carbon plus oxygen going to CO2, exothermic, at minus 393 kilojoules per mole. We have another reaction of carbon monoxide plus oxygen going to CO2 and is also exothermic. These are experimentally possible to measure. However, if we want the enthalpy of reaction of carbon going to carbon monoxide, it is nearly impossible to measure this directly. However, we can still determine its enthalpy of reaction by using Hess's law, which can be shown visually here. The enthalpy of reaction of carbon plus oxygen going to CO2 is minus 393, and the enthalpy of reaction of CO going to CO2 is minus 283. So we can take the first reaction forward and go down to the lowest level, and then we can take the second reaction backwards and go up to the intermediate level. And so you can see the first reaction is minus 393 as was given, but the second reaction is reversed, and so we reverse the sign, combine the two, and we obtain the desired reaction. Now we're going to work this problem where we're given three known reactions with their associated enthalpies, and we need to find the enthalpy of reaction for the unknown reaction. Before we solve the Hess's law problem, I want to show you some demonstrations of the chemical reactions. The first reaction is the combustion of acetylene with oxygen, producing carbon dioxide and water vapor. It is quite exothermic, as shown in this video.
Frankly, this one scares the hell out of me.
Boom! The next reaction is carbon plus oxygen gives carbon dioxide. And this can be shown in the laboratory using carbon that is hot plunged into a beaker filled with oxygen gas, and you can see the reaction is quite exothermic. You can also observe this on a more everyday scale when you light briquettes in your barbecue. And reaction number 3 is the combustion of hydrogen with oxygen gas to form water. Okay, so we're going to work this problem where the desired reaction is 2 carbon plus hydrogen to give us C2H2. And the strategy is to look at the reactants and see that we need 2 carbons. Reaction number 2 gives us carbon, but only one at a time. So we have to multiply reaction number 2 by 2 in order to get the desired reaction. So we'll take that guy and we'll multiply it by 2, and that's going to give us 2C plus 2O2 goes to 2C, try that again, 2CO2, and a delta H of minus 788 kilojoules. The next reactant we need is 1H2. Now reaction 3 gives us 2H2 every time it goes forward, so we need to multiply that one by 1/2 times 1/2. And so that looks like H2 plus 2 plus 1/2 O2 gives H2O, and that has an enthalpy of reaction of minus 286 kilojoules, which is half of the given. Now finally, in the products, we need 1 C2H2, but we're given in reaction 1 2 C2H2s as reactants. So reaction number 1, we have to multiply by 1/2, and we need to flip it over. That's going to change the sign. So we'll do that all in one step, where we get 2CO2 plus H2O gives C2H2 plus 5/2 O2, and the delta H with this is plus 1300 kilojoules, which is the opposite sign shown in reaction 1 and multiplied by 1/2. Now we can go ahead and add these all together and cancel out like terms. So there's 2CO2, those disappear. Here's one water and another water, those disappear. And here we have 4/2 O2 and 1/2 of O2, that makes 5/2, and here we have 5/2, so those can cancel each other out. And what are we left with? 2C and H2 and a C2H2. 2C plus H2 gives C2H2, and combining the delta H's gives us positive 226 kilojoules. As a final thought, I'd like to show you the difference between the forward reaction of the combustion of acetylene with its reverse reaction demonstrated creatively in the following video.